Hello students, welcome to the lecture number 6 on chemical bonding and molecular structures chapter. In this lecture we will be going to discuss a very important thing, that is the polarity of covalent bond. The existence of 100% polar bond or 100% ionic bond is a ideal state. Never happens basically. No bond or no compound is 100% polar or 100% ionic. Even the covalent bond formed between the hydrogen atoms also is found to be having some percentage of ionic character. So today's lecture we will be spending the polarity of covalent bond. Polarity of covalent bond. Means the covalent bond will have some percentage of ionic character that we will discuss how we can able to assess all those ionic character in the covalent bond. When the bond form between two similar atoms like hydrogen, like oxygen, like chlorine, like nitrogen, like fluorine, like iodines, at that time what is going to happen? The shared pair of electron is equally being attracted by both the similar nucleus, and the shared pair of electron will lie just in the middle of the two atoms. So in that time, this type of bond, when this type of bond is produced, when the shared pair of electron just in the middle of the two atoms, at that time we will call this is a non-polar covalent bond. So first thing that we need to understand, this is non-polar covalent bond. In just between the two atoms, two bonded atoms, two bonded atoms. So again, when there is a non-polar covalent bond, naturally some covalent bond that must be a polar covalent bond. What are those covalent bond? Polar covalent bond. When the shared pair of electron will be shifted towards an bonded atom, and that is happen when the two atoms which are producing the covalent bonds are not identical, means one of them having the higher electronegativity than the others. When it is so, then shared pair of electron will be shifted, will be distorted towards the more negative element. So where the shared pair of electrons shifted, so we can write for this polar covalent bond, shared pair of electron, so we can write that this is hydrogen with hydrogen. It will be the non-polar covalent bond. Hydrogen, then with chlorine, chlorine with chlorine. These are all the non-polar covalent bond. And what is polar covalent bond? In the time you can see there is a hydrogen fluoride. What is going to happen? Fluorine atom will attract itself the electron pair, and it will be slightly negative, and this is called the polar covalent bond, or you can say HCl. In HCl plus and minus. So what is going to happen? There is a creation of a dipoles. In both the polar covalent bonds, we can see there is a creation of dipoles. Creation of dipoles in this polar covalent bond, and it is also the polarity of the covalent bond can be measured by the difference in the electronegativity between the two atoms. Difference in the electronegativity, as for example, hydrogen has the electronegativity is 2 and 2.1, and whereas the fluorine has the electronegativity is the 4. So in that case, you can see there is a difference of the electronegativity, and higher the electronegativity, the higher will be the polarity of the covalent bond. All covalent bond is not polar, but there is a direction, there is a changes, there is a gradation depending on the difference in the electronegativity of this element. So if we compare, HF will be the higher bond of the HF will be higher polarity, bond of the HCl will be slightly lower polarity, because electronegativity is less here and here electronegativity is higher. So this dipole is now created, and how to measure these dipoles? Dipoles is measured by a very important factor that is called the dipole moment. That is called the dipole moment. So we will going to understand what do we understand that the what in which way we can able to measure this dipole moment. Dipole moment is measured by this mathematical formula, and it is expressed, dipole moment is expressed by a Greek letter that is mu. So dipole moment mu can be written as Q. Q is basically the charge developed, that is the positive charge or negative charge developed in the molecules due to the polarization. These things is called the polarization. When the electron cloud has been shifted towards the electronegative element, it is called the polarization of the electron charge towards itself, towards the electronegative element. This polarization creates these dipole moments, and this dipole moment can be measured by this charge on this, or the negative charge or positive charge, into the separation, the distance between the two atoms. That suppose it is d. So in this way we can easily able to calculate the dipole moment of the diatomic molecules. And dipole moments is basically, we will see, it is a vector quantity. Vector quantity means it has both, that is magnitude and a specific direction. And the specific direction we will understand how it is being denoted in the Lewis structure. You have to put a cross arrow in the Lewis structure, and that will going to represent the dipole moment in the molecules. And that is the way to represent the dipole moments in the molecules. That is by the crossed arrow. Crossed arrow means this is the crossed arrow, and this crossed arrow has been pushed to the molecules. The molecules having the dipoles. Here you will see the positive, that is the crossed side of this arrow has been put on the positive side of these atoms, and the arrow of this head portion of this arrow will be put in this negative side of this element. That we know it has, the dipole has been created, and in this way this is the vector quantity. In this way, a crossed arrow is put on the root structure of this molecule. This is how we can represent, because it is a vector quantity. So now we understand the dipoles, how the dipoles is created, what is the polar covalent bond, what is the non-polar covalent bond, and how this dipole created, and how we can able to measure the dipole moment for the diatomic molecules. But it is if it is a polyatomic molecules, then how do you calculate it? Now we understand it. Now we are going to discuss how we can able to measure the bond polarity of the dipole moments of the polyatomic molecules. Polyatomic molecules, like you can understand that H2O. H2O is a polyatomic molecules. In this case, there is a two bond instead of one bond that we have already discussed, and it is having the angle, bond angle is this. For the polyatomic molecules, we have to consider the dipoles of the different bonds. In the diatomic molecules, we have discussed, we have considered on the dipoles of the one bond. Here it is a two bond. Then at that time, what will going to happen? Suppose this is the bond polarity of the dipole moments of one bond is mu1 and another bond is mu2. At that time, the total dipole moment of this molecule will be the vector sum of these two dipole moments. And suppose in this case for H2O, the angle is 104.5 degree, but it can be taken as a general term. Suppose the angle between the dipoles, angle between the bonds having the dipole, angle between the bond is suppose theta. At that time, you can write the resultant dipole moment of this molecule is mu is equal to mu1 square plus mu2 square plus 2 mu1 mu2 and cos theta. And it is when this dipole moment can be represented in a parallelogram law. Parallelogram law, in this case we will observe this is the dipole, this is the resultant dipole moment, and you have this is one bond dipole moment and the other bond dipole moment, and you will get this resultant of this dipole moment by this and with this equation. Thus you put the dipole moments. If you know the dipole moment, then you have to put this and you will get this. Okay, as for example, you can take one example. Suppose BF3. For the BF3, the dipole moments, suppose all the bond dipoles is same. This dipole moment is directed in this, because fluorine is much more electronegative than this boron. So what is going to happen? The electron will be shifted towards the fluorine, and here the dipole moment, suppose it is mu, and this is also be mu, and this is also be mu. At that time, and their bond angle, we know it will be 120 degree bond angle. And we will observe one very important thing, their dipole moment will be zero, in spite of this fact that each and every bond dipole is much more adequate bond dipole, because the electronegativity difference between this very high. In spite of this, there is a high bond dipole, their resultant dipole moment will be zero. How that we can able to understand? I mean, if you put this resultant, you can see this resultant of these two dipoles bond dipoles is just opposite of these dipoles, and its magnitude will be same. So as it is a opposite, same dipole moment will be 0, and this dipole moment, if we calculate, you can find this will be mu square plus mu square minus half into 2, because cos here 120, cos 120 means half, so it will coming around mu. So you can understand this also have the same magnitude, and this direction the same magnitude, and it will cancel each other, and we are going to 0 dipole moment. So you can understand the dipole moment is an important parameter of this molecule that can predict us, that can help to predict us many things that we will now discuss. So the dipole moments can be, there is a different application. First application, that is the prediction of polar molecule, prediction of polarity of bond, polarity of bond. Very simple formula, simple direction, that higher the dipole moments mean, higher will be the polarity of the molecules. If the molecules have the higher dipole moment, then we will say that its bond polarity is high. As for example, you can take the example of the halogen acid. You can see hydrogen fluorides have the dipole moment is 1.98, and hydrogen chloride is the dipole moment is 1.07. Hydrogen bromide, its dipole moment 0.78, and hydrogen iodide, its dipole moment is 0.38. So you can see that when the dipole moment is decreasing, you can see the highest dipole moments having the HF, at lowest is having this HI, and that is because of this fact the bond polarity is the lowest in case of hydrogen iodide acid as compared to the hydrofluoric acid. So from this dipole moment you can able to understand the polarity of the bond, whether a molecule is polar or non-polar. That can be easily be find out by these parameter, very important parameters, that is the dipole moment. Second thing, we can also say about the symmetry of the molecules. Symmetry of the molecules that can be assessed by this dipole moment also. Some molecules will have the dipole moment 0. As for example, this is carbon disulfide, and its dipole moment, you can see the direction of the dipole moment is totally in the different direction, and the molecule is at the plane. So its dipole moment is 0, means this molecule is symmetric. Another example you can take for carbon dioxide. So carbon dioxide, you also find it is having the dipole moment is 0. So when dipole moment is 0, we will call the molecule is symmetric. So another example we can take, that is your methane. Suppose methane have the tetrahedral structure, but its dipole moment is 0. That is direction of the dipole moment of this bond, of this bond, and of this bond, and we will find the dipole moment is 0, because, and from this we can say this molecule is symmetric. Third point, we can say unsymmetry of the molecules. Unsymmetry of the molecules also can be assessed from the dipole moments. Some molecules have some resultant dipole moments. As for example, hydrogen, H2O. H2O, you can find there is a dipole moment, and its dipole moment, there is a 2 electron pairs, and it will have, the electron pairs will also have some dipole moment. This. So its dipole moment, it is found, it is 1.86 D. When we are talking about the dipole moment, we have to always give the units, that is dBi. Now, what is the units? Let us first understand. The dipole moments 1 dBi is 10 to the power minus ESU centimeter, and in the Coulombic term it will be 3.3 into 10 to the power minus 30, that is Coulomb per meter. This is the 1 dBi. So the units of the dipole moments is dBi, that is, when you write the dipole moments, you have to write the unit also. So here you can see H2 is having the dipole moment of 1.86. So in the dipole moment, the application of the dipole moment, we understand, you can predict about the polarity of the bond, whether the molecule is polar or non-polar. Number 2, that we can understand that a symmetry of the molecules can be assessed from the dipole moment. Number 3, from the unsymmetric molecules also can be assessed from the dipole moment. Then we can also predict, or we can say distinguish. We can distinguish, that is a third application, distinguish between the cis isomers, cis and trans isomers. How we can distinguish? Let us understand. From the dipole moment itself, we are taking the example of dichloroethene. Dichloroethene is an organic compound that we will learn later when we are on the organic chapter. This is the dichloroethane, and it is the cis isomers. Here you can see the polarity, bond polarity in this direction, bond polarity of the CH bond in this direction, and the chlorine is in this direction, and chlorine is in this direction. So in this case, what is going to happen? The bond polarity will be greater than 0. Whereas in the trans isomers, the position of the similar molecules will be at the diagonals. So in this case, what we will find that here the dipole moment is 0. For the trans isomers, this is the trans isomers, this is trans, this is cis isomers, and this is trans isomers. The trans isomers, it will be in the direction, in this direction, and its dipole moment will be 0. And from this you can able to say that from the cis and trans isomers you can able to easily distinguish between them. Cis isomers having their some specific dipole moment, whereas trans is 0. Same thing you can also say for these meta-isomers, para-isomers, and the ortho-isomers. For the suppose we are taking the dichlorobenzene. In the dichlorobenzene, what we will find, this is 1,2-dichlorobenzene. This is the ortho, and here also another isomers of it is meta isomers, and another isomers, that is para isomers. Both the cases, in three cases, you will find the different type of dipole moments, and from this also you can able to calculate, you can able to say the about its ortho, para and ortho, meta and para. Para will having the zero isomers, zero dipole moment, and meta will be in between these two. So from this dipole moment we can able to say about the para, ortho and meta isomers. So you can understand dipole moment is very important thing. Another thing that we are going to discuss, that is from the dipole moment we can able to say about the percentage ionic character of the covalent bond. Combination of ionic character in covalent bond. Ionic character in covalent bond. How you can calculate? Now you can calculate this mu, this is dipole moment, and it is basically the ratio of the actual dipole moment in the bond, dipole moment in the bond means observed dipole moment divided by the dipole moment in 100% ionic bond, 100% ionic bond into 100. From this you can able to calculate the percentage ionic character on the covalent bond. You can take one example. Suppose lithium fluoride, lithium hydride, its dipole moment has been found. From these two data we can able to calculate lithium hydride have the dipole moment is 2 into 10 to the power minus 29, and the lithium distance between the lithium atom and hydrogen atom is 1.6 angstrom. From this you can able to easily calculate this. First you have to actual dipole moment observed in the molecule you observe, that is this. So mu actual is given by a 2 into 10 to the power minus 29 coulomb meter, and you have to calculate the when the bond is 100% ionic. At that time how you calculate, already you know, Q into D, Q here when the charge will be developed, unit charge will be developed, then we can write 1.6 in 10 to the power minus 9 coulomb into distance it is given 1.6 into, we have to convert it into the meter, it will be 10. So this will be 2.56 into 10 to the power minus 29. Now ionic bond percentage, this is the, you can say ionic percentage ionic bond, you can write this percentage ionic character in this covalent bond is given by, percentage ionic character is given by mu actual, dipole moment actual divided by dipole moment on the ionic condition, dipole moment ionic, and into 100, and if we put all this value we will find it is coming around 78%. So this is a very important tool, that is dipole moment. From this we can able to calculate the ionic character, percentage ionic character in the covalent bond. Okay. In this way you can also calculate, you can also determine the different dipole moments of the molecules. As for example, I can give you one example that you can able to calculate the increasing. In the question it will be told arrange these molecules in increasing order of the dipole moments. NH3, NF3, then Ni3, NBr3, NCl3. In this case also you have to consider the dipole moments of the bonds and dipole moments of the lone pair electrons, and in this way you can able to calculate, and you will find that NH3 having the higher dipole moment, followed by Ni3, this will be followed by NBr3, followed by NCl3, and last will be the NF3. This will be the answer. Okay, that is all for today's lecture. So in this lecture we have discussed a very important thing, that is polarity of the covalent bond. Because any type of bond which is formed by the heteroatomic molecules, which is called the heteroatomic molecules, because both the atoms is different. At that time the bond formed by this molecule will have some amount, some percentage of the other characters. In the next lecture we will discuss the reverse thing, that ionic compound having some covalent character, and the Fajans rules we will discuss. So we will meet in the next lecture. Thank you very much for watching. If you like this lecture, if you like this video, you can share it to your friends. Thank you very much for watching.